Ranveer from Indian Institute of Technology in Gandhinagar. So I start introducing some preliminaries. First of all, we consider the set of integer points in the plane, x square. We consider the natural partial order, x square. We define the standard definition of intervals, that is the set of elements, the intervals, the interval AP is the set of integer lattice points bounded by A and B with respect to the natural partial order. In some part, we need also to consider not only integer points, but also real points. So in this case, we consider the closure of the interval. And in an interval, we can identify the set of vertices. So having in mind the picture of the interval, the set of vertices, the set of points A, B, C, D, while the set of edges is the set of unidimensional intervals like AC, like CB, like BD. For instance, okay. For instance, this one is an edge of the interval. When we consider a collection of intervals in Z square, we say that the set of vertices of the collection is the union of the set of all vertices of all intervals belonging to the collection. The same we can say the edge of the collection. It is important to mention that the smallest possible interval, that is the unitary square in Z square, is called a cell. So, roughly speaking, a cell is an interval of kind A plus 1, 1. I provide also the definition of polyomino. Considering a collection of cells, we say that two cells are connected if there exists a sequence of cells such that any two consecutive cells share an edge. If in a collection of cells, all couple of cells are connected, we say that the collection is a polyomino. In the figure in the left, you can see an example of polyomino. Because, for instance, if I take this cell and this cell, these can be connected using, for instance, this part of cells. And you can see that every cell shares an edge with the successive cell. And it is easy to see that these are holds for all couple of cells. In the picture in the right, you can see an example of a collection of cells that is not a polyomino. For instance, you can consider a cell here and a cell here. It is not possible to connect these two cells with a path of cells sharing each one an edge with the other one. Okay. In 2012, Qureshi introduced a way to associate a coordinate ring to a collection of cells. I explained briefly this construction. We have a collection of cells P. We introduce the polynomial ring whose indeterminates are indexed by all vertices of the collection. We define an inner interval of the collection, every interval such that all cells contained in the interval are contained also in the collection P. And to all inner intervals, we associate a binomial called an inner minor in this way. This binomial is the product of the variable associated to diagonal corner of the inner interval minus the product of the variables associated to anti-diagonal corner. We consider the set of all inner minors of a collection of cells, and the ideal generated by all inner minors is the ideal IP, also the ideal associated with the collection of cells. the coordinate ring of P is the quotient ring between the ideal and the polynomial ring. You can see in the figure an example of a collection of cells and the related ideal associated. For instance, you can see in the highlighted red part, you can see an example of inner interval that is that contains two cells, and what is the associated binomial inner to minor. For instance, in this case, the binomial x11 times x32 minus 12 times 31. Oh, this is another example. The other binomials are obviously associated to all cells or all the collection of cells, because every cell is also inner to minor interval. Okay. In literature, there are many papers that study this kind of ideals. In particular, the aim is to relate the algebraic property of the coordinate ring with combinatorial property of the polyomino ideal, or the ideal associated to a collection of cells. For instance, there are many known results about the primality of the ideal, about the Groebner basis of the ideal, or for instance also about the EVent function of the polyomino ideals. You can see something about in the next talk of Francesco Navarra, something about the EVent function. In this talk, in our work, we focus in particular in the problem of primary decomposition. So, to introduce this problem, I want to explain this example. This is an example of a collection of cells, and we compute with Macaulay 2 an example of its minimal prime. In this case, we can consider this minimal prime, that is the sum of these two ideals. Okay, two parts. That is, the first is a monomial part generated by variable. The second part is a set of binomials. Each one, the color is associated to the correspective colored interval in the figure. But we can see that not all these binomials are associated to cells, or at least this interval is not, this ideal is not an ideal associated to a collection of cells. So this suggests us to consider a more general combinatorial configuration to study the primary decomposition for ideal associated to collection of cells. So for this aim, we introduce the concept of folio collection. A folio collection is a collection of intervals, so not all cells, but also general intervals, satisfy the following property. For every couple of intervals belonging to the collection, if the intervals are I and j, then I is not contained in j, and vice versa. And one of the following property holds, that is, or the two intervals share a common edge. If not, then the intersection between all edge of the interval I and the edge of interval j is the intersection has cardinality no more than one. In figure, we can see two examples. The first one is an example of folio collection. The second one is not an example of folio collection, because if we consider this interval belonging to the collection and this interval belonging also to the collection, then the 1 and 2 are not satisfied. The 1, no, because their intersection is not the entire edge of the first interval, of the red interval, because they share a common edge. The second one is that the intersection is greater than 1. We have 2 points in common between these two edges of the two intervals. Okay, now introducing a polio collection, we want to generalize also the definition of inner interval. For a polio collection, we define an inner interval such that its closure is the union of closure of intervals belonging to the collection. We can see in figure, for instance, we can consider this interval. This interval is an example of an inner interval because it is the union of this one and this one. Okay, for me, this one belongs to the collection, this one belongs to the collection, and this one belongs to the collection. So their union, that is all these intervals, is an example of inner interval. But, for instance, this one, even if in figure seems that it is contained in the collection, this is not an inner interval. It's not an inner interval because it is not the union of its closure is not the union of closure of intervals contained in the collection. Because, for instance, for us, this interval or this one is not an interval belonging to the collection. The vertices of the collection here are the black points. So we have the definition of polio collection. We have a definition of inner interval. As for collection of cells, we can associate a coordinate ring. That is, we consider the polynomial ring such that the variables are indexed by all the vertices of the collection. For all inner interval, we associate this binomial obtained by the product of the variables associated to diagonal corners minus the product of the variables associated to anti-diagonal corners. We consider the set of all these binomials. We consider also the ideal associated with the set. This is called the polio collection ideal, and the quotient ring between the polynomial ring and the polio collection ideal is for us the coordinate ring of the polio collection. We can remark that if our polio collection, every interval is a cell, the construction is exactly the same as that provided by Qureshi. So this is actually a real generalization of the construction provided by Qureshi. I want to provide here also another example. This is an example of polio collection. We can see that not all elements in the collection are cells, because this one, for instance, is not a cell. We can consider the polynomial ring considering all vertices of this collection and the polio collection ideal associated. For instance, this cell is a trivial example of inner interval, and in this cell we can associate the corresponding red binomials. The same for this one. If we consider this one, this is an example of inner interval because it is the union of two intervals. In this case, two cells. In this case, the cell, the interval 3, 3, 4, and the interval 3, 3, 4, 4. So this is an inner interval. We have the associated binomial, and so for the other ones. So this is an example of polio collection. Another thing that I want to remark is that, okay, some polio collection are algebraically the same collection of cells, in the sense that some polio collection are the coordinate ring of some polio collection are actually isomorphic to coordinate ring of some collection of cells. For instance, the two collection in figure have the coordinate ring isomorphic. But this is not always, of course. For instance, for the polio collection I showed before, I share with you some sketch of this fact why this is not possible to find a collection of sets whose coordinate ring is isomorphic to the coordinate ring of this one. That's why, because for this folio collection, using also Macaulay-2, we can see that this is not a domain. The 8 of the folio collection ideal is 5 and is unmixed. The Krull dimension of this the coordinate ring is 9, and computing the minimal primes, we find some minimal primes that are a monomial ideal. That is a monomial ideal. This fact, together with a theorem by Herzog, Ibi, and Moradi, tell us that a possible collection of cells whose coordinate ring is isomorphic to this folio collection is a collection of cells having exactly 5 cells. So the possible collection of cells have exactly 5 cells and have to share this algebraic property. But again, using Macaulay-2 and some other tools developed in this paper with Francesco Navarre and Rosanna Tano, we can argue that the only collection of cells having 5 cells is unmixed. The coordinate ring is not a domain, and the Krull dimension is 9, is the collection of cells in figure. But computing the minimal primes of this collection of cells, we find that no minimal primes is a monomial ideal, against the previous that has a monomial minimal prime that is a monomial ideal. So the coordinate ring of these two collections are not isomorphic. So roughly speaking, the set of coordinate ring of collection of cells is strictly smaller than the set of coordinate rings of folio collection, also up to isomorphism. So the introduction of folio collection is like introducing a more general class of coordinate rings. Okay, so in order to give some insight about primary decomposition, we need to consider the lattice ideal. So I introduce briefly this construction. For a folio collection, we set n the number of vertices of the folio collection. So in Zn, we introduce for each vertex of the collection a vector Ba, that is the vector having coordinate equal to 1 in the coordinate corresponding to A, and 0 in all other coordinates. Now, for all interval belonging to the collection, we can associate a vector that is the vector BA plus BB minus BC minus BD, where A and B are the diagonal corner of the interval, while C and D are the anti-diagonal corner of the interval. This is a set of vectors, so we can for all interval of the collection, so we can consider the subgrouping Z of n generated by these vectors. This is the set lambda C, that is the lattice associated to the collection C. A standard construction in commutative algebra allows to introduce a binomial ideal associated to a lattice in this way. That is, considering a vector in the lattice, we associate this binomial. That is, okay, the difference between two monomials, where the first one has exponent vector, that is the set of positive coordinates of the vectors E, of the vector E, while the second monomial has exponent vector, the positivization of the negative coordinate of the vector E. Considering the ideal generated by all these monomials for all vectors belonging to the lattice, we define the lattice ideal associated to the collection. This ideal is important because of these two properties. The first one is that the polio collection ideal is always contained in the lattice ideal. Moreover, this ideal algebraically characterize the primality of the polio collection ideal, because the polio collection ideal is prime if and only if it is equal to the lattice ideal. And this is a good tool to study for what I introduce soon. Okay. So to continue, I need another definition, that is the definition of admissible set. First of all, consider that if we consider an edge of an interval AC, I call the boundary of an edge the bound of the edge. For instance, if I take, this is an interval, this is an edge. For instance, this is an edge, A and B. I called A and B the boundary of this edge. An admissible set is a subset of the set of vertices such that for every inner interval of the polio collection, the intersection between the admissible set and the vertices of the inner interval is empty, or contains the boundary of an edge of the interval. So, okay, I introduced this concept of admissible set. What is important is that to every admissible set, I can associate a set of intervals made in this way. That is the set of all inner intervals having non-empty, such that the vertices as empty intersection with the admissible set. And to such set of interval, J of X, I can associate a polio collection CX, because we are able to prove that this set GX is the set of inner interval of a polio collection, and I call this polio collection CX. So, summary, what is important is that I have this definition of admissible set. I am able to associate another polio collection that I call CX. I provide here an example for this collection of cells. For this collection of cells, the set of red points is an example of admissible set. I emphasize here the point, because, for instance, if I consider this interval, the vertices of this interval have empty intersection with our admissible set. But if I consider, for instance, this one, in this case contains the boundary of an edge. That is, contains, for instance, these 2 points. And so in this case, contains the boundary. Okay. So, okay, I have an admissible set, that is this one. To this admissible set, I can associate another polio collection, that is the polio collection CS. Okay, maybe I don't need no more this figure. So we can see, and the collection of cells is exactly the polio collection CX is the set of interval that are colored in this collection. Okay, so now starting from a polio collection, we take an admissible set. We consider the other polio collection associated to X. And okay, another thing I want to remark is that even if we start from a collection of cells, the polio collection CX in general is not a collection of cells. Is a polio collection in general. So this is that's why we need to introduce the polio collection. So I repeat, considering the Folio collection, considering an admissible set, considering the associated Folio collection to the admissible set, we can define this ideal, Gx. This ideal is exactly the sum of two ideals, that is the lattice ideal associated to the Folio collection Cx, and the monomial ideal generated by the variables associated to the admissible set. These ideals are important because for every, we are able to prove that for every minimal prime of the Folio collection ideal, we can find an admissible set such that the minimal prime has exactly this form. So every minimal prime is an ideal of this form. In general, the converse is not true. That is, not all these ideals are minimal primes. But anyway, we can say that the intersection of all these ideal Jx for all admissible set is exactly the radical of the Folio collection ideal. In particular, when the Folio collection ideal is radical, this second theorem provides a redundant primary decomposition. So this is is difficult because what will be very interesting it is to if it is possible to characterize what are the admissible set associated to the minimal primes. So to obtain an irredundant primary decomposition, a minimal primary decomposition. So in order to have some insight to go ahead for this question, we focus on study a specific collection of sets that I introduce now. This is the class of closed path polyominoes. A closed path polyominoes is a sequence of cells that I can index in this way, A1, an plus 1, such that the first one is equal to the last one. Every two consecutive cells share a common edge. Okay, all cells are different, and there are not, in a certain sense, near self-intersection. That is, if I consider a cell EA, cell AI, if I consider a cell AI, then all cells Ij with J belonging to this set of indices, the vertices, the intersection of the vertices is empty. Of the vertices of both cells is empty. Okay, you can see intuitively what I mean for closed path by these two figures. For instance, in the left we have an example of closed path, so a path of cells that is in a certain sense a cycle. In the right, we have not a closed path polyominoes because of this intersection. So this intersection does not allow to consider this collection of cells a closed path. So we focus only on the collection of cells of this kind. Okay, in order to go ahead, we need also this particular definition provided by Mascia, Rinaldo, and Romeo, that is a very formal definition that is called the zigzag walk. So I explain briefly what I mean for zigzag walk. A zigzag walk of a collection of cells is a sequence of distinct linear intervals, such I1, IL, having the following property. Every consecutive interval intersects in only one point. So we have something like this. It's better here. So intersect in only one point. This is the first property. The second property is that, for instance, this configuration is not allowed. Is not allowed because we want that the two consecutive intersection points should belong on the same edge interval. That is, this is not allowed because this does not belong to the same horizontal interval, but we need something like this. So something in this way. For instance, here, for instance, here, for instance, here. Because in this way, any two consecutive vertex in the intersection belong in the same horizontal or in the same vertical. So in this way, in this way. The third property says that, okay, these intervals are all inner interval, but we need that, for instance, these two inner intervals that I can consider between between a couple of the interval in the zigzag collection, these two must not be inner interval of the collection P. And the same for this. And this for all couple of intervals. So it is a very formal definition, but okay, we need, it is important to consider that we need this definition. Okay. Another thing that is important is that to every zigzag walk we can associate a binomial. A binomial is a binomial I write here in the right in the right. That is okay. Is the we can identify some vertices in the zigzag, for instance, in a sort of cyclic way. For instance, this one I call Z. I consider the product of the variable of these vertices, that is the first binomial, minus the product of the variables associated to these vertices, that is the second monomial. So also this one is a very formal definition, but okay, it is important to say that I have a zigzag walk. To every zigzag walk I can associate a binomial. And the binomial is constructed in this way. So this is the binomial. And moreover, to all zigzag walk, I can associate a subset of vertices that I call the necklace. That is the set of vertices in red. So this one, in a certain sense, is the, roughly speaking, the set of vertices in the inner perimeter of the zigzag walk. So we need the definition of this of necklace to collect together this vertex in a set. For zigzag walk, in this figure we have an example of two different zigzag walk of a closed path. The difference in this case you can see in this part. These parts are different. But the nice thing for closed path is that the set of necklace of two different zigzag walk are always the same. So actually, for a closed path, the set of necklace is uniquely determined. So this is another nice fact that is important for our results, for the results. Okay. Why zigzag walk are important? Zigzag walk are important because, as proved in this paper with Francesco Navarra, the primality of closed path is characterized combinatorial by the existence of non-zigzag walk. So a closed path is prime if and only if it does not contain zigzag walk. So in order to study the primary decomposition, we have to study closed path having zigzag walk. The second interesting result is that using a technique with Groebner basis proved in this paper with Francesco Navarra and San Aldano, This proves that closed path the polyominoid, the ideal associated closed path is always radical. So it is always radical. So if we remember this result, in this case we have that this set is exactly the intersection of this ideal Jx is exactly the ideal associated to the closed path. So for closed path, we know that the ideal is radical. Okay, so so we need to study a closed path having zigzag walk. Having zigzag walk combinatorially means that the only possible change of direction in a closed path is concerned with these two kinds of configuration, figure A and figure B. So in a closed path with zigzag walk, we have up to reflection or rotation different sub-configuration as these two. So we identify some vertices and binomials. In particular, we identify the set M of P, that is the set of all vertices like this one, appearing in all sub-configuration of the closed path, up to rotation or reflection. So in all possible appearing of this configuration. The set of all vertices of this kind is the set of MP. Then, considering the second configuration, in all appearance up to reflection or rotation, we associated this binomial. This binomial that is the product of the variables associated by these two minus the product associated to these two. So the second set, Rp, is a set of binomials associated to this configuration everywhere it appears in the closed path. And finally, we call N of P the necklace of the closed path. That, as I said before, it is uniquely determined by one zigzag walk, by one possible zigzag walk. So I use these three sets to define two ideals. The ideals are the ideal P1, that is the sum of the ideal associated to the closed path, plus the ideal generated by all binomials associated to the zigzag walk. I remember these binomials. So IP plus all these binomials. This is the first ideal I call P1. The second one, P2, is the ideal generated by the variables associated to the necklace of the closed path. The variables associated to the set NP, so I recall the set considering all these vertices, plus the binomials in the set RP. Okay, we are able to prove that these two ideals, P1 and P2, are both prime ideals, and both ideals have the same height of the folio collection ideal, that is equal to the number of cells of the polyomino ideals of the closed path. This means that actually these two are prime and they are also minimal primes of P, because it is not difficult to prove that the ideal associated to closed path is contained in both ideal P1 and P2. So they share the same height, so they are minimal primes. Moreover, considering that, as I said before, that the ideal IP is radical, using this lemma, we are able to prove that there are not other minimal primes. So actually, the ideal associated to the closed path is exactly the intersection of these two prime ideals. So P1 and P2 is provide exactly the minimal primary decomposition of the closed path. So for closed path, we are able to provide the minimal primary decomposition, and in a certain sense to characterize it combinatorially, because the definition of these two ideals is, as you can see, is combinatorially, because it is in the configuration of zigzag-Wolf, and it concerns with this sub-configuration. But now, how to link these two ideas to the first discussion? Now, the ideal P1 and P2 are indeed ideals associated to some admissible set. For instance, P1 is associated to the admissible set that is the empty set. The empty set is trivially an admissible set of a collection of sets, or anyway of a polio collection. While for the ideal P2, if we consider the monomial part, considering the set NP and the set MP, the union of these two sets, we can prove that this is actually an admissible set for the closed path. So, indeed, these two ideals are associated to some admissible set. And in particular, if we want to see better this admissible set Y, we can say that this is exactly P2, okay, I write here, and it is exactly the sum of the monomials associated to the admissible set Y, and the set RP is exactly the lattice ideal associated to the collection PY. PY is the union of these red intervals. So here the polio collection PY is a disjoint is in the polio collection PY contains exactly 4 disjoint intervals. So it is trivially a polio collection. Closed path allows us also to provide a counterexample of the fact that not all set JX are minimal primes, because considering this closed path in figure C, the set of vertices AB in this position is an example of admissible set. But if I consider the ideal JAB, this is not a minimal prime, because we can prove that it contains the minimal prime that is J associated to the empty set. So in particular, this example suggests that in some way seems that the admissible set associated to minimal primes are in some way involved to zigzag-Wolfs, but for this we don't know in this moment how they are involved. So this is in particular one of our main question. In this case, the question C, that is how is it possible to characterize the admissible set associated to minimal primes for a collection of sets, or more general also for polio collection? This is a good question in order to characterize or to provide combinatorially the minimal primary decomposition for collection of sets, or more general for polio collection. Moreover, I want also to mention some other known questions that arise in studying polynomial ideals and collection of sets. The first one, okay, for collection of sets, we know many properties about characterize the primality, the hyperfunction, and the Groebner basis, and about polynomials. So a possible direction to investigate is if it is possible to extend known results for collection of cells also in the case of polio collections. And the second one I want to mention is a well-known question about collection of cells, that the feeling is that all collection, the ideal associated with collection of cells is always radical, but it is not yet given. So this is a good question to ask for, to try to do this, or maybe also to try to find and study some classes in which the collection, the ideal associated with the collection of cells is radical. Okay, so that's all, and thank you for your attention.